Hi everyone, I'm Naifeng. I'm currently a fifth-year PhD student at CMU, advised by Professor Franz Branchetti. And today I'm going to talk about our work on semantics lifting for scientific kernels. So now let's forget all the coding experience you have and imagine you're a domain scientist. So imagine you're a domain scientist with minimal coding experience. Let's say if you're a physicist and you are deriving an algorithm, let's say for fluid dynamics. And there is a core scientific kernel, namely discrete Fourier transform, DFT, within your algorithm. And now you have everything down using pencil and paper, and now you want to write some code to test it out. So what would you do? So one thing I would do, and also many people I talked to yesterday would just tell AI to do this for me. So I would ask GPT to give me an implementation of the DFT. And this is what GPT outputs. It is a fast Fourier transform algorithm, FFT, to implement DFT in C. And now, please raise your hand if you know for sure this piece of code is correct or not. So I don't see any hands raised. And this is expected. Because for these complex scientific kernels, it is very hard to check for its correctness. And it's relatively easy to check for the syntactic correctness because now we have great compilers where we can throw this piece of code into the compilers and see if the compiler complains. However, it is very hard to check for the semantic correctness, which means how do you know this piece of code actually implements what you want? And how do we know this piece of code actually matches to the, for example, the math we derived on the paper? And this is the problem we're trying to solve. So our goal, which we termed semantics lifting, is to automatically extract these high-level semantics from these scientific kernels. And we do not stop at the ASD level. We do not stop at the program summary level. We go all the way up to the mathematical specification. We have 4 letters here to tell you it's a DFT. And if you were at the keynote, the first keynote yesterday, you heard Professor Amer's-Hing talking about this two-way street of compilation, where we have from high level to low level, that's the traditional compilation pass, and then we have the low level to high level, that's the decompilation pass. So we can treat semantics lifting as this extreme version of decompilation, where we go all the way up to the high level spec. And actually, today's keynote also further strengthened our motivation by Professor Kim when she talks about how important validation is in this area of AI. And semantics lifting can act as this first defense of this AI-generated code. So how do we do this? The key insight behind semantics lifting is that we have, let's say in the traditional compilation pass, we go from a representation A to representation B, from high level to low level. And if this rewrite rule is based on mathematics, and if going from A to B actually establish mathematical equivalence, then we have an equal sign, and that means we can go back. And this exists in many compilers and code generation systems. For example, in this code generation system called Spiral, that's been developed, I think, for over 25 years. And in Spiral, we don't need to understand the math here, but in Spiral, we go from one level of mathematical abstraction, which is the SPL on the right-hand side, to a lower level mathematical abstraction on the left-hand side called sigma SPL, which captures the loop level program structure, whereas the SPL captures more on the algorithm side. So my advisor did this traditional compilation pass 20 years ago at PLDI, and now I am flipping this direction around. And this is the key insight behind the semantics lifting work. So I don't think I have too much time to go into the detail of how, like the entire semantics lifting framework, but in general, we start with the source code, and then we go through all these already established IR within Spiral, level by level, and then eventually reach to this high-level specification. And of course, this is still a work in progress, and we also have many limitations. So one limitation, for example, as you can notice, towards the end of the semantics lifting, we lift everything up to a combination of mathematical objects. And then we do a knowledge-based lookup to see, does this match a decomposition, algorithmic decomposition of a DFT? And if so, we can derive, yes, it is indeed an DFT using this kind of algorithm. But let's say, what if you derive an algorithm that Spiral does not have prior knowledge? And it is okay because semantics lifting still provides value even if you don't reach the last stage. It is much easier to compare this combination of mathematical objects with your math on paper than comparing this source code with the high-level math. So we right now obtained some preliminary results. So we finished building up the prototype, which we can take a piece of C code, and then to derive it is actually a DFT, and it's using the Cooley-2-key fast Fourier transform algorithm. And we also test the robustness of this framework where, let's say, we flip around two independent instructions within this loop, which does not change its semantic correctness, but our system is able to tell you so. But however, if we change, let's say, I hope the font is big enough for you to see, if we change this 1 to 2, then the semantics breaks and the math breaks, and our system is also able to detect a bug. And semantics lifting, right now, we show an example of working on AI-generated code. But we don't need to, the source code can be anything. It can be a legacy code, let's say, written 50 years ago in National Lab in Fortran. And then we can use semantics lifting to derive its semantics. And then we can do re-optimization to make use of all these existing compilers, DSL, to target, for example, GPU. So this concludes my presentation, and you can scan the QR code if you want to read the short paper on this, and my email is here if you have any feedback or comments afterwards. Thank you very much.
Questions?
Are there any limitations in how programs can use recursion where this technique might fail to derive a closed form, anything like that?
Right. So currently, I would say there are, if we go back to this framework, there are limitations at each step. And I talk about the limitation at the end of the lifting, but of course there are limitations how we what kind of source code we can lift up to. So right now, we start with the harder part. We try to lift a recursive implementation of FFT, but for the loop-based FFT, we can also lift that up. And I think one thing we cannot do, for example, using Spiral, is to lift up some source code that use a data-dependent computation. Thank you.
Could you give me some insight into, I didn't really understand how the system worked from the talk. Can you talk about how it's built up, how you're doing this kind of decompilation or this?
Right. Yes. Sorry, for the sake of time, I omit lots of details about how the system works, but only providing the key insights. So if we go through all the steps here, so first what we do is we take the source code, we use clean to dump the AST, and then we reparse it into this internal code that is the lower level IR the Spiral understands. And then from this lower level code, we try to impose a normal form where, for example, in this loop, we have the load, compute, and then store this pattern. So that's the gather, the G, what G stands for here, the gather, compute, and the scatter pattern here in the math. And then after we are in the math domain, we can then use this key insight to reverse these rewrite rules and step by step all the way up to the high level spec.
So does this require that fundamentally what you're implementing is some simple closed form mathematical expression or something like that?
Yes, and everything for the semantics lifting is symbolic. And right now, we really take advantage of all these existing rewrite rules that has been injected into Spiral over the past 25 years.
Thanks for the great talk.
Thank you.
One thing that's unclear to me is in this figure, which of these things existed previously and what is the contribution of?
That's a great question. So within Spiral, all the arrows where we go from DFT to these rewrite rules to the icon and then to the source code, this existed for the past 25 years. And this is the code generation part. So what I did is I did all the arrows back all the way up to the specification.
Great talk. So I'm interested in knowing where else this technique can help. For example, compiler optimization. They always go from top to down, but they never come from down to up. So do you think this technique can help to discover some new optimization in compilers?
Oh, so how does this technique help with the compilers? That's actually a very interesting question. I think definitely. So for example, when I mentioned that, let's say the legacy code in the national lab, which is probably a lack of documentation there. But let's say I bet there are many like very talented domain experts who inject those knowledge within these kind of code. But these right now is unmaintainable because there lack of automatic way to derive what has been injected there. And if semantics works on this kind of code, we can actually derive many specific, let's say the formulas here, that we can then put down into the lowering paths so we can take advantage of that.
Yeah, and another thing could be we always lose debug information when we go from higher level to lower level, and we have to do a lot of engineering to come from lower level and map it back to the source code. So maybe something like this can help.
Exactly. Thank you.
Thank you.
All right, that's all the questions we have time for. Let's thank the speaker again.
Thank you very much.